Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, combinations. So we get n and k, and we want to return all possible combinations of k numbers that we choose from the range 1 to n. And this answer, we can return it in any order, so it doesn't have to be in a specific order. So if we take a look at this example 4, that means we need to choose numbers from 1 to 4. And then we need to find all combinations of two elements. So yeah, that would be 1 2 1 3 1 4 2 3 2 4 3 4, right? Those are the only possibilities. And so we actually want to return the combinations themselves. And the number n here is really small, it's just 20. So this tells you that you should be able to use some recursive solution, even if it's 2 to the power of n or n to the power of k, or whatever exponential in terms of the parameters here. So yeah, that means in this sort of problems where you sort of have multiple possibilities that you need to find, usually are solved with backtracking. So let's see how we can do it. Okay, so how do we tackle it? So looking at n equal to 4 and k equal to 2, what happens? So if we just consider this a list 1 to n, then we would have 1 2 3 4. Okay, so what can we do? Well, for each element, let's just take an index over this list, and just for each element take it or leave it. Okay, so if we do that, then let's say here first we decide to take 1. I starts out as 0, of course, and so we decide to take 1. And so we have now, so basically initially this is the list of the remaining elements, and then we would have the elements that we chose. But we also need to have I, which is this index. So now initially I equal to 0. So this sort of is the state. Initially I equal to 0, the list, we have everything, and then we have the chosen elements. Okay, so if we take this, then first we choose to take index 0, and so now we are at index 1. We have the remaining elements. Remember, because we don't take an element multiple times, it's each element is taken only once. We keep the entire, we remove the element that we taken. If repetitions were allowed, then we don't remove it, right? We will keep 1 here. So that's just to get you thinking about how to handle different backtracking scenarios. Okay, and what's the chosen now? Well, we just chosen this element 1, and so we just put it. Okay, if we don't choose 1, so this is choose, this is not choose. Okay, then we still go to the index 1, but we have all the elements still there, and we have empty for chosen. Sorry, not all the elements. We remove it actually, even if we didn't choose it, because otherwise we will never choose 2 if we keep it. And then we keep doing this, right? So now we do this for I equal to 2. So here we choose 1 or we don't choose it. So if we choose it, we end up with chosen containing 1 and 2. And then the remaining are 3 and 4, and now we are at index 2. If we don't choose it, we just have 1, and then we have remaining 3 and 4, and then we are at index 2, and you get the idea. We keep going like this, and here actually we stop because k equal to 2. So whenever k equal to 2, we stop, and this is a solution. So we add this to our result. And we'll keep going here as well. So let's say this also has 2 choices, choose or not take or not take. So if we take, we have 4 remaining, and we have 1 3, and now we have a solution. So we add it to our result. So we add 1 3 now to our result, and we keep going like this until we are done. So this is one way of doing it, and this is what's the time complexity of this solution. It's just a recursive solution. Well, we are doing 2 choices each time, 2 decisions, and what's the height of the tree. So for a solution like this where it's recursive and there are decisions, you just need to know how many decisions and what's the height of the tree. So each time we do 2 decisions, and the head of the tree is at most the number of elements, right? Because each time we reduce that by 1. Okay, so that means the number of levels is going to be at most n. So it's going to be at most the number of elements, which is n here. Okay, and so for this decision solution or recursive solution, the time complexity is usually the number of decisions you make each time to the power of the height of your tree decision. And so in this case, since the number of decisions is 2 and the height is n, it's 2 to the power of n. Okay. Now there is one detail here about this chosen array, because we will need to copy it, and so if we copy it, it's going to add another additional n, but that's a detail that we can look at later. So this is the first way of doing it. Another way, okay, actually let's see the other way of doing it later, but one thing I want to note here is we don't actually need this entire all of these states. We can actually, instead of passing the index and the list, we can just pass the number. So first we pass 1, and then on the next iteration, since we will need to process 2, we pass so let's call this x, we pass x plus 1, which is 2. The next iteration we pass x plus 1, which is 3. Because as you saw here, each time here we looked at 1, we decided to take it or not. Then we looked at 2, decided to take it or not. Then we looked at 3, we decided to take it or not. And then we'll look at 4 and decide to take it or not. And so, because we don't need repetitions, if we follow the order from 1 to n, then we won't repeat any k elements. We won't repeat any single elements in our chosen list. So another way of doing it is actually just using a state where you have x, which is the element we are looking at, and then the chosen what we have so far. Okay, and so that way we'll start with 1 and empty, and then we decide to take it or not. And so if we decide to take it, we have 2 and 1. If we don't decide to take it, we have 2 and empty. And similarly here for 2, we decide to take it or not. If we take it, it's going to be 1 and 2, and you get the idea. If we take it here, it's going to be 2 for the chosen array. If we don't take it, it's going to be empty. Okay, and then we decide for 3, and then we decide for 4. So that's sort of the idea here. Yeah, so let's code this solution up and make sure it passes. Okay, so let's code it up. So we need to pass x and the chosen elements so far. When are we done? Well, we are done when we have k element in chosen, right? We return, but we need to add this chosen to our list. Okay, and then we need to define that list that we return at the end here, and then we need to call the combination, of course, with initially element 1, and the list is initially empty. And then what we do here, we have 2 choices, either take or skip, right? Leave. Okay, so here if we take, we go to the next element and then add this current element to chosen list. If we skip and leave it, we don't add it to the chosen list, pretty much, and that's the only difference. Now, when are we done? There is another way we are done here, is when x reaches n, because remember, we want to go just from 1 to n. So here, if x is actually bigger than n, then we don't want to add anything. We want to stop. Okay, so that's pretty much it. Pretty straightforward. And it gets accepted. Now, one thing I want to mention here is that this is not efficient, because each time we are creating a new list. So what we can do here is just append to the current list, but and then when we finish the recursive call, we want to pop x out. So we want to pop this element out. So we pop it. Now, one thing then here, because we pass the list itself, we don't copy it. We want to copy it here so that we don't change it for the next iteration. Because if we just don't copy it and pass it like this, then the next iteration that appends or pops will change this list that we already added, and that's not what we want. So we want to copy it. And in Python, to copy it, we do this. So if we run this again, Looks good. Let's submit. And looks like it got accepted. Okay. Now, another way of doing actually this solution is, remember what we want is from 1 to n. So instead of making two decisions, right, when we are at x, right, let's actually do multiple. So let's say when we are at 2, at 1, for example, well, we have multiple choices. We can choose 2, 3, 4, 5, 6, 7, 8. So we can choose, let's say for k equal to 4. Let's take for k equal, n equal to 4 and k equal to 2. So for 1, we can choose up to 4. So we can choose these. Okay, if we choose 2, then we have 1, 2, the list 1, 2. If we choose 3, then we have the list 1, 3, and you get the idea. Okay? And then once we are at 2 here, we can take 3 or 4, right? And so that would be basically, here we end up with 2, 3 or 2, 4, okay? And similarly for 3, we have only one choice, which is 4, and so we would get 3, 4. And so for each element, we have at most k decisions for which elements to take. And so again, using the number of decision to the power of the height, the number of decision is each time at most n, and the height of the tree is at most k because we stop when we get 2 elements. So it's going to be n to the power of k. And so to do that solution here, we just call this x, but what we do here is we do a loop. So we do a loop for, let's say, call it next in the range of from x. So for example, for 2, it's from 2 plus 1 to n. So it's from x plus 1 to n. And n is inclusive. Okay, so for that, we choose or not choose. So, okay, so we do like that. And this is equivalent to the previous solution because if we don't choose, not choosing next will just happens on the next call, right? And so here we can just remove this. Okay, so we also want to change this to be next, right? That's the element we want to take, and same thing here, next. Now the other thing here, we don't want to pass 1 because we will start from, we add from the next one, from x plus 1, so we want this to be start from 0. And I think that should cover it, so let's try it. Looks good, let's submit. And that passes as well, okay? And as we said, this is of nk, and then if we take the copying here, it's going to be n, it's actually going to be k multiplied by n to the power of k because of the length of chosen can be up to k. Okay, so with this solution, it's actually better, but we can also do another optimization. So one thing you saw in this tree that I did here is that this 4 here doesn't have any children because there are no elements after 4. And so how can we get rid of this one? So the way we can get rid of it is we can just check here if the number of if n minus the length of, so if k minus the length so far of chosen, so what basically this is what's remaining, what we need, still needed, or call it remaining, then, or needed, then what do we need this to be? Well, we need this to be smaller than what we still have, which is this range. What is this range? Well, this is n minus x, I think, plus 1, or n minus x, right? Okay, if it's bigger, then that means there is no solution because you want to have enough element to get k elements, and that happens here for 4. But it's more clear if you have like k equal to 4 and you have only 2 remaining elements, you can't construct the solution, so there is no need to go to that path. So here we can say we can prune. This is called pruning your tree, your backtracking tree. So if k minus the length of the chosen so far, so what we need still, if that's bigger than what we have left, then we want to return, and stop proceeding. So if we submit, see, this still works, right? Yeah, so that's, I think, pretty much it what I wanted to cover for this problem. Please like and subscribe, and see you on the next one. Bye.